Hello! In part 2 we have seen that a varying base emitter voltage caused by a varying transistor temperature is causing a varying current into the collector. After the intro we will extend the circuit in such a way that even with a big varying collector voltage, the collector current will remain very stable. Today we will discuss a current limitation or current control with two transistors. In part 2 we have seen that with a stable base voltage and a temperature caused variation of the base emitter voltage, the voltage on the current sense resistor is also varying, and this causes a varying current E. To solve the problem, we introduce a second transistor with a low current through it, and this current is also not too much varying, so that we have a low and more or less equal power at this transistor. This causes a stable base emitter voltage on this transistor, and with the stable voltage we measure the voltage on the current sense resistor. The circuit works as follows. Case 1. Assume the current will increase a little bit. Then the voltage at resistor R2 will increase. This will cause that the transistor T1 opens a little bit more. This will cause a bigger voltage drop at R1. With the bigger voltage drop at R1, the voltage at the base of transistor T2 decreases, and he will close a little bit until the original current is restored. Case 2. The current E will decrease a little bit, then the voltage at the current sense resistor will decrease a little bit. This will cause that the transistor T1 will close a little bit. This will cause that the voltage drop at resistor R1 will be smaller, so the base voltage on the transistor T2 is higher, and it opens a little bit until the original current is restored. Now let us calculate the circuit. We assume we want to have 10 milliamps output current. The current should be stable from 1.4 to 37 volt. The control voltage should be 5 volt, that we can use later Arduino Uno to drive this circuit for a constant current LED chain or a shortage protected output. And from the datasheet we know that the minimum current amplification is 200. The base current for T2 is the current divided by the amplification factor. It's 10 milliamp divided by 200 is 0.05 milliamp. Now we calculate the cross current of the controlled voltage divider built up with resistor R1 and the transistor T1. The cross current is 10 times the base current. The cross current is 10 times 0.05 milliamp is 0.5 milliamp. Now we want to determine the voltage at the current sense resistor R2. It's equal to the base emitter voltage of transistor T1. For this we need the datasheet. Here is the reference to the datasheet. And with the cross current in the collector of T1 we can determine we have 0.5 milliamp collector current, and we get 0.63 volt base emitter voltage, which is the voltage at the current sense resistor R2. In the same diagram we can find for the 10 milliamp collector current at transistor T2 that we need a base emitter voltage of about 0.73 volt. Now we can calculate the voltage drop at the resistor R1. At the control voltage U, minus the base emitter voltage of transistor T2 minus the voltage drop at the current sense resistor R2. It's 5 volt minus 0.73 volt minus 0.63 volt. It's 3.64 volt. The resistance of R1 is the voltage drop at R1 divided by the cross current. It's 3.64 volt divided by 0.5 milliamp. It's 7280 ohm. If we have these resistor values available, we will select the next smaller one to ensure that the cross current is at least 10 times bigger than the base current. We select for R1 4.7 kilo ohm. Now we calculate the current sense resistor R2. It's the voltage drop at R2 divided by the current E. It's 0.63 volt divided by 10 milliamp is 63 ohm. If these values are available, we select 27 and 33 ohm and connect them in series, so we add them and get 60 ohm for the current sense resistor. This is our complete setup. We have the collector voltage supply U1, which can vary from 1.4 to 37 volt. We go through an ammeter through T2. T2 is a BC547B, and through the current sense resistor R2, which is built up with a series connection of a 27 ohm and a 33 ohm, and go back to the collector voltage supply. The control voltage U2, which is 5 volt, goes via the 4.7 kilo ohm resistor and the transistor T1, which is a BC547B, and back to the control voltage. The node between R1 and the collector of T1 is connected to the base of T2. The node of emitter T2 and the resistor R2 is connected to the base of transistor T1. During our experiments, we measure the current E, the collector emitter voltage of transistor T1, and the voltage at the current sense resistor R2. The capacitor C1 should be in the range of 10 to 100 nanofarad and avoid oscillating of the circuit with long supply lines. Here our measurement setup. The variable collector voltage goes via the ammeter via the red line to the collector of T2. The base of T2 go via the 60 ohm resistor to the ground line, and from the ground line via the blue line back to the variable collector voltage supply. The 60 ohm is built up with the 27 ohm and 33 ohm resistor. The 5 volt supply go via the yellow line via the 4.7K resistor to the collector of T1. The emitter of T1 goes to the ground line and via the black line back to the 5 volt supply. The node between the 4.7K resistor and the collector of T1 goes via the green line to the base of the transistor T2. The node between the emitter of transistor T2 and the 60 ohm resistor goes via the red line to the base of transistor T1. Here we have our 100 nanofarad capacitor between collector of T2 and ground to avoid swinging. With the red and blue line we measure the collector emitter voltage from T1 and show it here. And with the red and black line we measure the voltage at the current sense resistor from 60 ohm and show it here. For our first measurement we let the circuit for at least a half an hour unpowered to ensure that all devices and also the silicon in the devices gets adapted to the ambient temperature. Then we turn on the collector voltage to 1.4 volt and the control voltage to 5 volt. Then we measure immediately the values to ensure to get the values for a junction temperature which is equal to ambient temperature. I turn on the circuit now. I measure 10.41 milliamp at the collector from transistor T2, 1.332 volt at the collector emitter from transistor 1, and 629 millivolt at the current sense resistor. The next measurement we start after 10 minutes while the collector voltage remains on 1.4 volt. Then we increase it quickly to 37 volt, wait 10 minutes and go back to 1.4 volt and wait also 10 minutes. The circuit has now thermally stabilized with 1.4 volt collector voltage and we increase now to 37 volts. The circuit has now stabilized at 37 volt collector voltage and I will set it now back to 1.4 volt and wait again 10 minutes. We summarize our data. The ambient temperature was 20 degrees Celsius. At the first measurement we had 1.4 volt at the collector and all parts were adapted to ambient temperature. The current sense resistor voltage was 629 millivolt. The collector emitter voltage was 1332 millivolt and we calculate a base emitter voltage for transistor 2 of 703 millivolt and we measure a collector current of 10.41 milliamp. After 10 minutes with 1.4 volt collector voltage and all parts have thermally stabilized, we measure current sense resistor voltage of 626 millivolt, a collector emitter voltage from transistor 1 of 1325 millivolt and calculate a base emitter voltage of transistor 2 from 699 millivolt. The collector current is 10.39 milliamp. When the circuit was thermally stabilized with 37 volt collector voltage, we get the current sense resistor voltage of 624 millivolt. A collector emitter voltage of transistor 1 was 1197 millivolt. We calculate the base emitter voltage of transistor 2 with 573 millivolt and measure a collector current of 10.37 milliamp. During the whole measurement, we recognize the minimal collector current of 10.32 milliamp and a maximum collector current of 10.42 milliamp. Now we calculate the accuracy. The minimum current was 10.32 milliamps, the maximum current was 10.42 milliamp. The mean value of these two values is 10.37 milliamp and we get the delta of plus minus 0.05 milliamp. The relative change in percent is the absolute change divided by the mean value multiplied with 100 is plus minus 0.05 milliamp divided by 10.37 milliamp multiplied with 100 is plus minus 0.48%. This is a very good value for such a simple circuit. Now we check whether the junction temperature remain within the specification. The ambient temperature was 20 degrees Celsius. The base emitter voltage of transistor 2 was 703 millivolt at cold condition and 573 millivolt at the warm condition. So we have a delta base emitter voltage of minus 130 millivolt. The delta temperature of the junction temperature is delta base emitter voltage divided by minus 2 millivolt per degree Celsius is minus 130 millivolt divided by minus 2 millivolt per degree Celsius is 65 degrees Celsius. The junction temperature is the ambient temperature or the junction temperature at cold condition plus the delta temperature is 20 degrees Celsius plus 65 degrees Celsius is 85 degrees Celsius. This is pretty below the maximum allowed 150 degrees Celsius junction temperature. That the temperature constants of T1 is very important for the current constants in this circuit we can easily see when I warm up the T1 with my fingers. When I warm up, the transistor became warmer, the base emitter voltage gets lower, and with the lower base emitter voltage the current goes down. If I release now the transistor cools down and the base emitter voltage grows up, and with this current grows up. As we have seen, semiconductor devices can have a wide change of some of the parameters with temperature. This is the reason why high-precision measurement devices and calibration devices need an air-conditioned room where the temperature is controlled in a very small temperature window. Furthermore, these devices need a 1 or several hours warm-up phase before high-precision measurements can be done. This warm-up phase is necessary to get all internal parts thermally stabilized. That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. Bye bye.